Good morning, everyone, and welcome. It's a real pleasure to welcome Bryce Richards to give our seminar today. So Bryce is a professor at Karlsruhe Institute of Technology, KIT, in Germany, and Bryce has worked on luminescent approaches to improve PV efficiency and to give additional function to PV devices for about as long as I've known Bryce. So Bryce did his PhD here at UNSW. He then postdoced here when Martin Green had the Center for Third Generation Photovoltaics, and that was when he started working on down conversion. So Bryce has had a very distinguished career. He's got a few slides where he'll tell you all about it, but he's traveled the world. We overlapped a bit in the United Kingdom,
exactly. Yeah,
which was a lot of fun. And so, Bryce, it's a pleasure to welcome you back to UNSW.
Thank you.
We're really looking forward to hearing about everything you've been up to using luminescent processes for solar energy harvesting.
Okay,
Bryce.
Cool. Great. Thank you, Ned, for the kind introduction. Thank you for all turning out at fairly short notice. So it's much appreciated. Okay, so what I'll be talking to you today about is what I generally call spectral conversion technologies. So this is where you use luminescent materials to alter the wavelength of sunlight, and in the hope of maybe making your solar cell perform better. And I'll give you one example at the end of how you might also use that in a different application, but still involving solar. A little bit of an overview, what I want to go through today. 2 slides briefly about my academic journey, because it's been a bit tortuous, as Ned commented there. A little bit about where I'm from, Karlsruhe and KIT now, the motivation why you might want to do this. 4 different spectral conversion processes, so up conversion, down conversion, luminescent downshifting, and then the luminescent solar concentrator technology. Before then touching on this other solar technology, which doesn't really involve PV for me at least, which is on next generation greenhouses. So you might hear, I'm not Australian, I'm a Kiwi, or at least I was originally until my accent got changed a bit over the years. After spending a year at the Max Planck Institute in Germany, that's where I was working on amorphous silicon for solar cells. And that really caught my attention. Then I thought, wow, where can I study that? And the answer was UNSW. So I came back here, did a master's. My project was with Alistair Sproul, PhD with Chris Honsberg and Francesca Ferrazza, who was then at Eurosolare in Italy. And then Martin offered me the postdoc opportunity after my PhD, and he gave me the opportunity of working on luminescence, particularly up conversion, or on the hot carrier solar cell. And I was just saying to Ned before, I don't know if I made the right choice, but I chose up conversion. My journey then took me one step further. I was trying to find an academic position in Australia. I went to ANU for 1 year. Before getting a position at Heriot-Watt University. That's sort of like the number 2 university in Edinburgh. And on the way there, I spent a 5-month sabbatical at the ETH in Switzerland, working with a Yodia Tawari who works on CIGS and CAD-TEL solar cells. And you'll see as I sort of rose up the ranks at Heriot-Watt, I also took a kind of a different sabbatical and went to Tanzania for 18 months. Now, at that stage, I knew the position in Germany was going to happen. I just underestimated how long that might take. Academic processes are a bit slow in Germany. So then, from 2014, I've been working at the KIT in Germany. So where are we? That's a map of Germany. Karlsruhe is located at the northern end of the Black Forest, so in southwest Germany, not too far from Stuttgart. And if you hear Black Forest and you think of this, yep, that's the one, okay? You got the right place. And Karlsruhe, some people find it a little bit hard to say, but if you break it down, it was a city designed in 1715 by Karl Wilhelm III, and he wanted his Ruhe in German. He wanted his peace. So in other words, he wanted to build a palace where he could have his mistresses, while 5 kilometers down the road, the Queen was sitting in the old castle, and that's how he managed his life. Karlsruhe, just a few random facts for you. It was actually the place where a baron invented the first steerable bicycle. It had no pedals, but it was the first bike you could steer. And interestingly enough, why were these invented at this time? Because people were slaughtering horses. Why do you slaughter horses? Because you're running out of food. So it was a time of famine that prompted this technological invention. Fast forward another century or so, KIT was the first place to receive an email. It's sort of recognized as the true email because it was sent via a computer network, and it was sent from MIT back in 1984. More recently, anybody who has done any direct laser writing, so a 2-photon polymeric lithography process, might know the company Nanoscribe, who are now exporting machines over the world. That came out of KIT. But probably now, looking towards solar, some of you who are older in this audience might recognize Professor Peter Würfel, who was a long-time and very groundbreaking solar cell physicist based in Karlsruhe. Some of you may know his book, The Physics of Solar Cells. And he was also responsible for exporting this guy. Yeah, some of you might recognize here Torsten, who appeared in Australia quite a while ago now, before I left. And I had the opportunity to collaborate a bit with Torsten there. And then where are we today? What is KIT today? Well, we're kind of unique in Germany because we are a merger between a national lab, which used to do nuclear research only, so that's not the case anymore, and the Technical University of Karlsruhe. And they brought those things together in 2009. Now, this means we have a lot of staff. We're probably the largest research center in Europe. We have over 10,000 staff. Number of academics isn't huge. It's 415 professors. And also you'll notice the number of students, I guess, is probably less than half or something of what's at UNSW. So we're fairly small student-wise. These are the two campuses here. So the campus south, as we call it, is the old university part. And this is right next to the palace. And campus north, where I am mostly based, this is kind of stuck out in the forest. And why do you do that? Well, it was because it was a nuclear lab. So they figured putting it 10 kilometers out in the forest where nobody could see it was a good idea at the time. So a little bit about what I do now. So I lead a rather multidisciplinary team of physicists, material scientists, inorganic chemists, electrical, mechanical engineers, and we're all motivated about the links between light and materials, but not just on the fundamental level. We really like to pursue things where we can scale these up from materials to devices to systems. Oops. And what we do is kind of covered here in a very broad snapshot. So we started by doing a lot of nano and micro texturing of materials for light in-coupling, out-coupling. Optical spectroscopy, we have a couple of really nice optics labs for understanding transitions in materials. I'll skip that one. Hybrid solar technologies is a new direction we're pursuing, where you're probably familiar with the classic combined PV thermal technologies, but more recently putting a lot of effort into passive daytime radiative cooling. The luminescent materials are covered here. These could be microscale phosphors, maybe emitting in the visible, maybe emitting way out into the infrared, depending on what the application is. And some of these also we do at the nanoscale, engineering these core shell nanocrystals. We go a little bit beyond into applying these materials for photocatalysis. So this is borrowing from photovoltaics and then kind of looking what we can do specifically with regard to water treatment. And the water treatment work is actually what I did while I was in Tanzania. You'll see the photo there with one of the volcanoes in the background. But what I'm going to be talking to you today is highlighted in this yellow box, and this is mostly about these spectral conversion technologies. So where did this start? This started with brainstorming conversations with Martin about pushing the limits of photovoltaic devices. A lot of this on this slide is not going to be news to you. We have typically a 33% efficiency limit of a single junction solar cell under the AM1.5 spectrum. For crystalline silicon, this is lower due to Auger combinations, so more like 24. And amazingly, this record device is now coming out with 27.8% efficiency on large areas. So already 95% of what is possible via theory. And I find this actually amazing. So what options are there for boosting the performance of crystalline silicon beyond this? Sorry. So to answer that, we take a look at the losses in our system. Firstly, you have these thermalization losses here. This is governed by the band gap of your semiconductor. Anything with more than that results in lattice thermalization, relaxation of the carriers back down to the band edges, i.e. heat. And the other area where we could gain a lot is the transparency. So these are sub-bandgap photons in our system. So spectral conversion started out with having these two big goals. For down conversion, we would like to halve the energies of these high energy photons that I've marked here in blue. And up conversion, we would like to somehow sum the energy of these lower bandgap photons together. So the processes kind of look like this. Here, on the top, the up conversion showing two photons coming in, ideally one photon coming out. This is a very hypothetical band structure shown here. And in the case of down conversion, which is sometimes called quantum cutting, here we want to have only one photon coming in, typically UV blue, but we would like to have two photons coming out, ideally that are above the band gap of the solar cell. So here we could be ideally talking about photoluminescence quantum yields of up to 200%. This is like an external quantum efficiency in optics terms. And here for up conversion, we would typically expect something about 50% maximum. The third process is a classic, what I call luminescent downshifting, is a classical Stokes photoluminescence process. So one photon in, one photon out. The quantum yield won't be greater than 100%. So how can it help us? Well, I'll give you examples where it helped in terms of overcoming poor short wavelength EQE performance of some solar cells. And I'll also allude to stability at the end of the talk. And then using luminescent downshifting, if you put this in a polymer waveguide here, as shown here, these are PMMA sheets, 10 by 10 centimeters. You see that you get a nice optical concentration of light around the edges. And this is the luminescent solar concentrator that I'll talk about briefly as well. So I'm sure that you've heard of tandem solar cells, and probably specifically perovskite silicon tandem solar cells. So these are the big promise at the moment for overcoming limitations in silicon performance, where you have the high bandgap perovskite stacked on top of a low bandgap, in this case silicon device, as shown here. This is also being pushed a lot in Germany, and perovskite silicon tandems are now reaching nearly 35%, albeit still on smallish areas. So here, although the efficiencies are very encouraging, there's careful bandgap engineering required, or engineering of the whole cell, because typically these are connected in series. Upscaling remains a bit of a challenge for the perovskites, although there's products coming out now on the market. And finally, I think my biggest concern there is stability issues. So you've got the perovskite solar cell on the front side of your stack, and it will be seeing all the high energy light. And then if we kind of contrast that with what would be possible with spectral conversion. So here, this is not an optoelectronic approach. It's purely passive and optical, where you've got one layer of a material trying to modify the wavelengths of sunlight to better suit the properties of the solar cell that you already have. So you need to add one more layer to the front of the solar cell in the case of down conversion, and up conversion, it's one layer to the rear. Current matching is not an issue because you essentially still have a single junction photovoltaic device. Stability on the front side, I'm just trying to point that out here. Stability on the front side of the solar cell is critical. This is typically good for inorganic materials. It's typically more challenging for organic materials. And we even have looked in the past at the possibility of these front side layers then being retrofittable to PV modules that are in the field. This is something you obviously couldn't do if you were going to build a tandem. So luminescent materials, this is a very general slide. What some of the materials I'm going to be talking about today. There's a wide range of them available. Mostly I'm going to be talking to you about lanthanide or rare earth based phosphors. Other options in the inorganic world include semiconducting nanocrystals and quantum dots. Occasionally we use fluorescent organic dyes. These we're not making. These we are buying commercially. You can see some of these on the right, some of their optical properties for absorption and emission. These are the phosphors down below here. And the other thing that we sometimes resort to is kind of a hybrid material. So where you have the best of both worlds, hopefully, in that you have strong absorption from organic dyes and around the side. And in the middle, this is a europium ion. And europium is a classic red emitter. So here you can strongly absorb light and then emit it with a nice sharp peak. I'll show you some examples of that later. So the rare earth elements, lanthanum to lutetium, they kind of slot in here in the periodic table of the elements and are usually expanded down below. They have a very unique electron structure. Their 4f electron shell is partially filled, and this gives the materials very unique optical as also magnetic properties, not that that affects my research. The advantage here is that typically you can get very high photoluminescent quantum yields. The materials are relatively abundant. I'll have one slide on that shortly. They're non-toxic, stable, can be low cost, although this depends on supply and demand. The disadvantages are classically that they are typically very weak absorbers because the transitions are largely forbidden. And currently, some of these elements are listed on critical or strategic materials lists. Like in Europe, we have the EU Critical Materials Act, and some of these materials can be problematic depending on if they have another purpose that they could be used for. So I'm not sure what happened there. Okay, so this was the one brief slide about abundance. You can see these are the rare earth elements shown here in blue. And elements either side are lead and tin. So they're pretty similar in abundance to lead and tin. And right, now this is the famous Diecker diagram for rare earth elements, and it shows you what the energy levels look like in this material. It's kind of overwhelming at first, but after you learn to play with it a little bit, these turn out to be, you can approach these a little bit like an artist's palette. You have different colors that you can play around with. Maybe one that you might be familiar with, so the neodymium ion I've highlighted there. This is very often used in lasers, lasing very nicely at 1064 nanometer. And why? Because you have this unique energy level structure where you have this 4-level system, which is really good for lasers because you don't get reabsorption of your laser emission. But we won't be doing too much with that today. We're largely interested in this ladder-like structure of erbium. Now, erbium you might know as well from telecommunications, largely used for at 1550 nanometers. And here what you notice is the ladder-like structure enables you to have a 980 nanometer photon, putting a electron in an excited state, and then you can do that again and you reach another another excited state. And that's the kind of thing that we were interested in, because then this helps us to achieve this up conversion, where we could have 2 lower energy photons coming in and a green one, in that case at about 540 nanometers coming out. Now, that's not very useful to silicon because silicon is already absorbing 980 nanometer light. But it turns out you can do the same for 1550. So you can have 1550 photons coming in, 2 of them, they add together, and you can get a 980 nanometer single 980 nanometer photon coming out. Now, this sounds more useful. Let's see what we can do with that as we explore up conversion. So basically, to harvest sub-bandgap light, from an engineer's point of view, what do you want to do? Well, you want to take a bifacial crystalline silicon solar cell. you'd like to slap another layer on the rear of that, which contains your erbium-doped upconversion material. And then to stop the luminescence escaping, because luminescence is typically isotropically emitted, you just put some kind of reflector on the back. It can be PTFE or a sputtered metal layer if you want. Now, we did after we'd done a lot of the work, we did a quick reality check. So this is more like a post-mortem than a reality check, now that I realize it. But to ask, can this really work? And there's this great German word, I love it. It's called Jein, yeah? It basically means yes and no in the same word. Isn't that great? So, yeah, the yes of this is that, well, of course, we can integrate layers pretty easily on the rear of the solar cell because we've got a kind of transparent architecture there, at least transparent for the photons of wavelengths that we're interested in. And the nein side of it is like, well, due to the albedo of the ground, if you've got this array here, you're getting probably somewhere between 10%, maybe even up to 25% reflectance off the ground, and you are going to be harvesting those photons in that scenario that I've shown there. Of course, if I start putting layers and reflectors in that on the rear, I'm not going to harvest those anymore. My device is now opaque at the rear. So that's kind of the catch. That's kind of the benchmark here. So what would the potential gain via upconversion be? Well, if we're harvesting some of these photons in this 1550 nanometer band, and it takes two of them, I have to add two of those together to go up to 980, to hop up to here, then the answer will be roughly about 2.7 milliamp per centimeter squared enhancement in your JSC. So that's where we'd ideally like to be. So let's see how close or far we get from that. So erbium-doped phosphors. These are classically made in a fluoride dope host. Here I've shown you sodium yttrium fluoride. And why? Because this material has a very low phonon energy. So your lattice vibrations, your phonons, there you really want to minimize those because they can facilitate non-radiative recombination. Whereas here we only want to maximize our radiative recombination. So these are micron-sized phosphors in this case. You can't see the scale bar there, but they're about 5-10 microns across. And these are embedded in a polymer layer that we put on the back of the solar cell. So this was the first work that I started working on as my postdoc, and I was working with Avi Shalav, who was a PhD student at the center at the time. And we were kind of assisted by Torsten, who ensured us that theory says that you can have 40%, you could have a 40% efficient solar cell if it was combined with this upconversion layer. So we thought, great, let's try this. Now, we did know one thing, in that it's a non-linear process. Maybe to explain that, I'll hop on to the next slide. Ignore the text at the moment, but just look down here at this energy band diagram. So you can imagine what's happening here is that light is absorbed by this erbium ion at about 1550 nanometers. And then it donates its energy it's able to donate that energy to another neighboring ion. Now, if that neighboring ion is also excited, then you can go up the ladder and you can start summing your energies together. Now, of course, that depends on the lifetime of this excited state. If the lifetime of this excited state is limited, this will drop down and energy will just populate this state instead. So you're not really adding them together. So lifetimes here are kind of critical. And the lifetimes of the rare earths, typically something about milliseconds, which is fairly long for luminescent materials. So this is the first device that Avi and I built. And here is the EQE spectrum. Now, I want to warn you, this is not a classical EQE spectrum of our device. Why? Because the y-axis is logarithmic. Yeah? So the cool thing is, we managed to demonstrate that a upconversion silicon photovoltaic device could respond at wavelengths from 1480 to 1580. Hey, that's pretty cool. It didn't work really well, though. I mean, the peak of the upconversion efficiency was about 3%. That means the actual efficiency of this device we couldn't measure, like an IV curve or whatever. We couldn't resolve an efficiency. So this was all done with a laser, but if we put it under sunlight, actually white paper worked better. Yeah, I don't say that here. It's not written on the slides, but that was the case. So then we started, this is more recently now, about 5 years ago, we started to say, well, look, really, what are the efficiency limits here? Is there any hope? So we put quite a lot of work into a chemical reviews article where we examined the photophysics of upconversion applied to crystalline silicon PV under sunlight. And then we also extended that to look briefly at the potential for perovskites, other technologies, as well as photocatalytic systems. And the whole paper was basically about solving rate equations, where we try to maximize upconversion. And it turns out there's the key one. That's what I put here with this key conclusion. So for upconversion to even start to become efficient, we basically need about 100 times enhancement in our generation rate. Our generation rate, G, the number of photons coming in the AM 1.5G spectrum. We need at least 100 to start to see something ideally more like 1,000, and then it might start working quite well. So most obvious way to do this is you think, well, I can take lenses, mirrors, whatever, and concentrate the light. Yeah. So we just increase the photon flux via solar concentration. And it turns out if we do that, and we say, well, we go from 1 sun up to 1,000 suns, then kind of the required lifetime that we need in our system turns out to be a little bit over 1 millisecond. And this is actually feasible because I mentioned before the lifetimes we're working with are indeed about of the millisecond basis. So we had an EU project, and this part of this work was done together with Jan Goldschmidt when he was at the Fraunhofer in Freiburg. And we utilized the concentrics PV technology, which is essentially about 100x, or it's a 94 suns concentration we measured under a Fresnel lens focused down onto our solar cell, which had the upconversion layer mounted behind. And this kind of box here is just a reflector to try and reflect all that luminescence back. And then what we measured was a enhancement in JSC of about 17 milliamps per centimeter squared. Remember, the number sounds a lot, but remember it's nearly 100 suns, okay? The EQE we measured was a bit higher than before. It was now up to about 8%. And we were actually able to measure an overall energy conversion efficiency enhancement of about 0.5%, which was kind of cool. But it's sort of like you're just measuring something, yeah? What about going further? Well, like I said, that was nearly at 100 suns, but you really want to go to something more like 1,000 suns, where we'd have 10 times more photons, and our nonlinear process would work even better. But as you may be aware, silicon is not the choice of material for concentrating photovoltaics. And above about 100 suns, somewhere up to about maybe 200 suns, your Alger recombination really kicks in, and it makes these some kind of solar cells impractical for use. Just showing some data here. 27.6% efficient solar cell made by Amonix at 92 suns, and that's dropping quite a lot by the time you get to 400 suns. So there's no real point starting there. And also there's no point really looking to 3.5 solar cells either. But why? Because they're typically triple junctions at least. They have germanium or InGaAs layers on the rear, and they already harvest those sub-bandgap photons that we're targeting. We thought briefly about doing sensitization. So what that is where we see in our spectrum, there's a region there where we're not absorbing these photons. What could happen there? Well, there is the possibility of using other metal ions, for example, nickel, which can absorb in this 11 to 1400 nanometer range. They can pass the energy to the ytterbium ion, which then does the upconversion. But a quick look at the maths, and yes, you can probably double the number of photons you're getting in your system, but you're not going to get a factor of 100 enhancement that we would be looking for. Some other groups, this is coming from Peter Balling's group in Denmark. They were looking at plasmonics to enhance local densities of states. They demonstrated 10 to 100 times improvements, which is quite cool. But this is all typically done on the nanometer scale volumes. And I remind you before, I said that the rare earth materials were weak absorbers. So although here you measure a nice enhancement here, what happens at the end of the day is that you would actually need to repeat this structure over a large volumetric depth. And this kind of becomes challenging to do this. Let's say if you needed to go at least 100 microns, perhaps up to a millimeter in thickness. So it's not something we tried. This is from the literature. This again was a collaboration with Jan Goldschmidt, where we looked to put upconversion materials inside a Bragg stack. So this is your classic high-low refractive index stack. This is the high refractive index was an ALD grown titanium dioxide layer. And here you see lots of little points. These are nanoscale phosphors that are inside a polymeric layer that was spin coated. So we kept on jumping back between the spin coater and the ALD system, which wasn't very elegant, but it worked. What we managed to demonstrate was a 4 times increase in the upconversion quantum yield. But because we switched to these nanocrystals, the amount of absorption in our system was even less than we had before. We'd gone from having a solid mass of phosphor to now a diluted phosphor in a polymer system. So the absorption was still really weak. So where does that leave us for upconversion? So upconversion works really well under laser excitation. It works a little bit. You can demonstrate something working under sunlight, but at the end of the day, the sun is not a laser, and it looks pretty challenging what's required. You probably need 1,000 times boost in this, either the photogeneration rates or some of the other kinetic transfer rates in the system. And it probably involves a combination of these. We kind of tried solar concentration and we tried these nanophotonic structures, but maybe if you brought all those things together, it might start to work well. And what I didn't tell you, the results that we have so far, they were all on untextured silicon solar cells. And you think that's strange. Why? Well, because you don't want the scattering, right? We wanted the light to pass straight through. But you can't buy untextured silicon solar cells, okay? Fraunhofer can make them for you. You can probably make them here, but they're not very common, right? So this is not great either. In the review article, we did point a definite pointer towards organic materials. So this is something that both Tim and Ned have looked at in the past, so-called triplet annihilation upconversion. Where low excitation thresholds have been demonstrated, so a low amount of suns would be needed. A little bit the challenge there is that the energy conversion is limited out to about 1,200 nanometers, to my knowledge. So it's not quite relevant for crystalline silicon yet. It would need to start going beyond that to get to those sub-bandgap photons that silicon is currently missing out on. And as a final reminder, probably the JSC gains that you need would have to at least be greater than 4 milliamps per centimeter squared, because that's what you'd get, let's say, worst case from a 10% albedo in a bifacial module. So now I jump to down conversion. Down conversion has a long history actually in the world of fluorescent lamps. So there was a time when people were trying to get rid of mercury lamps, and they switched to xenon, but they found out that xenon was less efficient. So they were trying to boost the efficiency or the brightness of the lamp. So they developed these phosphors based on this PR. This is praseodymium, the praseodymium rare earth ion. And it has a band diagram shown here. What they were doing is they were exciting here with UV light, and then they would get 2 photons emitted, or 1.4 photons on average on this process. And this was done in the early 70s by people working at Philips and Osram and GE, companies like that. Now, when I said UV, it's actually deep UV. Yeah, it's 185 nanometers. So it may be relevant to space, yeah, where the solar spectrum starts at 120, but it's not relevant to the terrestrial solar spectrum. Now, the advantages is that down conversion should be a linear process, not this non-linear process, which is pump intensity dependent, like up conversion. And we were advised once again by our friend Torsten, and he's also told us that the number for this combination down converter on top of a silicon solar cell, it should also be 40% efficient in theory. So the disadvantages are, as most of you in this room will know, if you start to play around on the front side of a solar cell, you've got to be really careful, okay? It's really easy to screw things up, and to any kind of scattering or parasitic absorption or that you introduce could actually easily make your solar cell worse. And your materials that you're putting on the front of the solar cell, ideally they should be stable for decades. And why? Well, because you all know that silicon PV panels are sold with 25, 30, even up to 40-year warranties now. So manufacturers do not want to take a risk when they put something on the front. Now, it changed a little bit there. There was crystalline silicon, and now I'll just highlight that there's one slide involving germanium in my slide deck today. Why germanium? Because we were developing some materials based on our experience with erbium. I'm back to erbium again. And we observed that if we excited erbium in the violet or blue or green regions of the spectrum, shown here, black is the UV excitation, and this brown color is the green excitation, you can see that we started to measure quantum yields of about 150%. So that means when we shine a photon in on that color, we're getting 2 photons out in the near infrared. Now, I'm saying near infrared broadly because there is a small emission peak at about 1,000 that would be relevant for silicon, but most of these are coming out from the erbium peak at 1550. So for that reason, to demonstrate the technology, we took a germanium photodiode. We couldn't find any solar cells, so we had to get a germanium photodiode from Thor Labs. And then putting that under a solar simulator, OneSun, we were able to demonstrate a small, but I would say significant current improvement of about 0.6 milliamp per centimeter squared. But of course, that's not really where we want to be because that's not relevant for silicon. So then we jump back and look at some works of other groups of what they have done for these materials. So there's an excellent luminescent materials group at the University of Utrecht, led by Professor Andres Meyrink. There they were developing phosphors that would be able to absorb UV blue light, and using the same praseodymium ion but a different wavelength range, they were able to demonstrate that they got about 1.4 to 2 photons. It wasn't quantified exactly. It wasn't a quantum yield measurement there, but that the energy of these 2 processes from here to here and here to here, they got given up to these neighboring ytterbium ions. And the ytterbium ions, they only have one energy level. It's a simpler system, and they would emit at 980 nanometers. So they demonstrated this. It worked. The catch is that the absorption here, once again, it was really weak. It was about 10%. So in subsequent work, they then created a dye-sensitized nanocrystal system where they added a coumarine dye, which was doing the absorption job in the UV and emitting in the blue. And then it transferred the energy from the singlet state of the coumarine across to the rare earth ion. And there they measured a intensity enhancement of 30%. But again, quantum yields weren't measured, so we can't quite quantify this accurately. And then in about 2017, 2018, the Gamelin group in Washington in US, they published this material system based on a perovskite, which some people here in the room working on perovskites might recognize, cesium lead chloride or bromide, and again, doped with ytterbium. The ytterbium is there for the same reason I said last time. This should be a nice emitter out at about 980 or 1,000 nanometers. This luminescence is well absorbed by the silicon. And the absorption, because it's a semiconductor, this should be quite strong. And you see there's 2 options there. I'm just showing the chloride and the bromide because of their different band gaps. And there's a little bit of a magic how this is meant to work. So when you put ytterbium into this system, it sits in the place of lead, but lead is 2+, and ytterbium is 3+. So this creates some defects, but these defects were somehow magically meant to help this process work. So the energy transferred from the conduction band of the semiconductor across to these defects, at which point, again, the energy was given up simultaneously to 2 ytterbium ions, which are somehow in close proximity. So results seemed really encouraging. It didn't really matter so much about the bromine concentration. You can see here any of these blue curves, whether it's 0%, 20%, or 40% of your bromine, they all work pretty well. And a spin-off company was started out of this called Blue Dot Photonics. They exist still today, and they claim that you have 16% more energy coming out of your photovoltaic module with their magic additions. Our own ray tracing simulations indicate that if you took one of the Longi heterojunction solar cells that are the record devices today, you indeed could boost this up to maybe something around 31% efficiency. So pretty impressive. Now, there are a couple of catches. So the first catch is that, and the authors in Gamelin's group mentioned this themselves, they actually discovered that their system was indeed nonlinear. So i.e. as the amount of absorbed photons increased, which I've shown in that graph, the quantum yield dropped from the near 200%, which they'd claimed, to being something around 100% at what you would get under 1 sun. And if you go to higher concentrations, it just then falls further. The second odd thing is that even after many years later, there was no evidence of solar cell EQEs being published. For me, this is kind of a hard proof. They showed it nicely here. They show a layer on top of a silicon solar cell, but nothing's been published. So after scratching our heads a while, we had a joint project with Professor Rebecca Seev at the University of Twente in the Netherlands, and we spent a couple of years recreating this material system. You can probably hear from my tone, yes, indeed, we failed to achieve 200%. In fact, we got about 1/10 of that. We got just over 25%. Yes, it did 25% was about the best material we could make. Now, at this point, I'd like to emphasize that a quantum yield measurement, or photoluminescence quantum yield measurement using an integrating sphere is an absolute measurement. And an absolute measurement means you have to be super careful of your calibrations. So we are wondering whether something in their system perhaps was not well calibrated, but we're still trying to solve this issue. It's an issue that's been encountered by other groups around the world. There's a group in Monash making similar materials. They were very excited. They asked us to measure the quantum yields. They were also far from 1, far below 1. What is cool, though, is that in the meantime, a new assistant professor at the University of Utrecht, a guy called Freddy Rabouv, has developed a technique based on photon counting or photon bunching experiments. And what he's doing there is he's shining a photon in using ultrafast systems. Photon comes in, and he looks for the correlation of a photon coming out. And in a classical photoluminescent system, so this would be luminescent downshifting, you'd expect 1 in, 1 out, 1 in, 1 out, and there'd be a simple correlation. In a down conversion material, and he chose this one here, you expect 1 photon coming in, and indeed, he expects 2 photons coming out, which he measures. So now we at least have some tools to be able to measure if down conversion is the true process or not. So there's a bit of a partway summary on that topic. There's been some exciting results reported. Repeatability seems to be a big issue there. So the demonstration of a greater than 100% EQEs on a silicon solar cell is still missing, and especially doing that under full sunlight. These photon bunching measurements are giving us a cool tool to be able to look at these materials more closely. It's not only about measuring a quantum yield, but you can actually understand more about the mechanisms involved. I've commented on the need to avoid parasitic absorption in your system, because otherwise you could make the overall performance of your solar cell worse. And at this point, because I come mainly from the inorganic world, a nod to the organic material people here in the audience that yes, singlet fission is kind of the similar process, where you would like to, in that case, inject multiple triplets into the silicon. So it has the same end effect. The process is very different. Again, probably the challenge there is that you're putting organic materials on the front side of the solar cell. Could be challenging for long-term stability. So if we can't achieve 200% quantum yields, or not yet, what can we achieve with less? So there are plenty of materials available. Some of the organic dyes I showed before that we use, the quantum yields of these are very close to 100%. You can debate whether they're 98 or 100%, but they're very close. So with my first PhD student in Scotland, we started putting these luminescent downshifting layers on top of different solar cells. And what was the motivation at the time? And I think that's captured on the left graph quite nicely, where you notice that all the quantum yields of devices at the time, they were all pretty bad. Yeah. So this was 2009 we started this work. So it's quite a while ago now. The only one with a decent EQE, but it still ended at 350, was the device from SunPower. Yeah, SunPower were one of the few companies making high efficiency cells back then. Blue is the multicrystalline silicon. Red is a CIGS device that I won't talk about more today, but I will talk quite a bit about this device here shown in black, which is cadmium telluride. And you can see its response is actually miserable up until about nearly into the green. Here you've got a quantum efficiency of 20%. So we started putting these dyes into layers on top of the solar cell. And for example, what I've shown here is a violet dye from the BASF Lumigen series, where you can absorb the UV quite nicely, and it emits out, as the name would guess, in the violet or in the bit into the blue region. So that means that you can kind of hopefully try and overcome a poor EQE in this range and shift that to a region where the solar cell is responding better. A patent came out of this work where we discovered that you could actually put these dyes quite nicely into the pre-existing EVA encapsulant that's used in the silicon encapsulation layers. So there were no additional production steps. This would be a standard laminate going in, and in our case, you would have one layer of luminescent EVA instead of the standard clear EVA. What this showed, we got a small absolute efficiency enhancement of 0.2 to 0.3%. So remember, devices were less efficient back in the day. So we're talking about going from, I think it was 16.3 to 16.6% efficiency, okay? Because the results are a little bit old now. And you can see here that you can actually measure an enhancement in the device EQE once you add this layer on top. That was the violet dye. We did it for many dyes. I've shown 3 here. That's what a mini module looks like. So a single 10 by 10 solar cell all laminated up. This is with the violet dye. This is a yellow dye. This is orange. You can see that as you go to some of the longer wavelength dyes, you start eating into your EQE spectrum of your solar cell, which would be that black line there. So what that means is you're actually taking away photons that would have been perfectly well utilized by the underlying solar cell, and you're kind of causing a bit of a problem on top. So these were not as efficient. Only the violet dye offered a overall net benefit. So just to jump back here, what one issue here is that we're absorbing photons here and we're emitting them actually not too far away. The wavelength shift is not enough. You'd rather have the emission way out here somewhere in the red, where the quantum efficiency of the solar cell was higher. So we started a joint research project with Professor Neil Robertson from the University of Edinburgh, where he was making some of these rare earth complexes. So what we can achieve there is actually materials that have a really large Stokes shift. So the difference in the peak of the absorption band, which is down here in the UV, and the peak in the emission band, which is out here in the red. So this antenna-like effect gives us strong absorption here. The quantum yields were up to 86%, which we were both really pleased about. And you get this nice red emission, and that's shown here in some sheets of PMMA. Now, the catch is that when we all went to the lab, when we went to the laminator to make the module, everything came out colorless. So what we'd done is during the lamination process, we had thermally degraded the molecules that Neil made. So I can't remember the temperature, something like 130, 150 degrees. His complexes didn't survive that temperature. Now, the news was a little bit better when we started working on cadmium telluride. So a lot of you will know First Solar, and back in Germany at the time, there was one of the second solars, and their name was Karlsruhe. And we were working with Karlsruhe to try and boost this terrible performance, the short wavelength performance of their solar cells. Yeah, so the black line shown here in the EQE spectrum. Now, it's a little bit trickier with a cadmium telluride device because this is a superstrate technology, which means that they start from the glass, that sunlight and everything else gets built off the back of that. So you have no real way of accessing the light before it reaches the solar cell unless you go on the outside, which is what we did. So we started extruding. We upscaled our research. We started putting some EVA and dye mixtures, extruding sheets that were about 0.6 millimeter thick, and then putting these on top of the soda-lime glass and with another fluoropolymer layer, a very thin layer, about 100 microns. Put that together as a sandwich and then put that into the laminator. And this gave us some quite cool results. Again, this is using organic dyes. So you can see here a range of all different dye mixtures. We had a violet, the violet only, and then we added a yellow and green and whatever dyes. The best performance enhancement was about 9%, which actually we were really happy with, and so was the company. So what we did then was that we decided to scale this up. So we scaled up to 1.2 by 0.6 meter modules, which is standard for CAD-TEL. And then we got a 4% enhancement. The process didn't go so well. There was still an improvement, which was nice. But in the meantime, something else happened, and that was they were needing investors, and they had to focus on their core business. Their core business, what was that? Trying to improve the quantum yield of their solar cell from this, which we had started with, and 3 years later, they had achieved this. So it got significantly better. And when the quantum yields get better in this region, then the potential for this luminescent downshifting technology actually gets worse. So I've just said that, the first point, luminescent downshifting gains are greater when the solar cell has a poor EQE, so there's fairly limited opportunities today. I did indicate how you can integrate some of these materials into an existing encapsulation layer or cover sheet. Probably the biggest use for the technology, and I didn't include any results here, but it's about enhancing the photostability or the lifetimes. So this has been proposed for organic, for dye-sensitized, and more recently perovskite silicon solar cells. But also I would point out that silicon heterojunctions, this is a work we started working on late last year, silicon heterojunction PV cells also exhibiting significant UV degradation. And then this layer overlying that could help solve that issue. Final topic, luminescent solar concentrators. This is taking some of the same materials and putting them into this waveguide. What's the attraction there? The attraction there is the same that has always captured the minds of people who want to work on CPV, concentrating photovoltaics. CPV should work really well when the cost of the optics is cheap and the cost of the solar cells is high, right? That's mostly why you don't see much CPV research going on in the world at the moment. So we were looking at this. Yes, the cost of the optics was cheap. The PMMA was 1 to 2 euros per kilo. The dyes weren't so cheap. Notice this is not a kilo, it's a gram. Yeah, 5 euros per gram, but they're fairly strongly absorbing. You don't need that many of them for a square meter. And the cool thing about this concentrator, and I usually have one in my bag, but I don't have my office bag with me, is that no matter which way you hold it, if I had one here in my hand, yeah, the light would be concentrated at the edges regardless. Yeah. So in the solar sense, this is cool because it's one of the only concentrators that can work under diffuse sunlight. So no tracking is needed. So it's a low concentrating system. It's not the 100 to 1,000 that I mentioned before. Probably somewhere to 5 to 10 is kind of optimistic here. And this is often pitched as a kind of an electric window technology because they don't want to compete with PV directly. They say you could have this window installed in your building. Yes, it would obviously have some color in it, your window, yeah? So let's see how that looks. So we started making these, a PhD student at the time in Edinburgh. He made some, what at that stage, I think they were the largest LSCs that had been made in the world. They were 60 by 60 centimeters. They had an optical concentration of nearly five times enhancement, which is good, but the efficiency was pretty low at about 2%. Some of this work carried on in a collaboration with GE Global Research, who used to have a lab near Munich. And they were interested in making 3D kind of roof tiles. You see them there. It's like corrugated iron sheeting, but made out of PMMA with this luminescent solar concentrator technology. And there we were looking at the lifetime of these materials. And indeed, this red Lumigen dye is expected to last about 10 years in the field. Many of the other dyes are lasting significantly less. So that's a kind of a challenge there. And the nice thing here is that although I can't say too much because GE owned all the results, there are some quite nice photos about how they benchmarked the technology of luminescent solar concentrator against many other technologies at the time. And then we did some ray tracing simulations to find out, well, what are the real showstoppers here? And the results show on the graph here that you can indeed get up into this red region approaching 10% with the 10% efficiency with the luminescent solar concentrator if you fulfill one or two criteria. On the y-axis here is the photoluminescence quantum yield, and you can see it matters, but it doesn't matter drastically. What really changes things is what's called the overlap integral, and again, note logarithmic axis on the x-axis there. And once you get to large sizes, this is now for just over 3 by 3 meter, which could be typical for, let's say, architectural glazing, a really large sheet of material. There this overlap integral gets critical. You go from the mountain down to the bottom of the ocean very quickly based on this value. Now, to graphically illustrate what that means, this overlap integral, you have to look across to this graph. So you want to be somewhere, let's say, below about 0.001. And that's the overlap integral between your emission spectrum and your absorption spectrum. And 0.001 corresponds to this green curve here. So this is a perovskite coming in. And all I did here was, the material was a perovskite, and then I artificially shifted the absorption band just to create a different overlap integral, okay? So it has origins of reality, but I have faked some of those steps. But just to point out here that the green band, which your eye would say there's no overlap at all. Yes, this is the kind of materials that you need. So, as Monty Python said, now for something completely different, but it's only one slide. What are we doing on this today? Ironically, the topic of one sun solar pumped lasers, yeah, is a hot topic in Europe, yeah? I can't explain why, but I have 2 grants in that area. And what is that? It's like having a frisbee. This is a 30 centimeter frisbee. It's a luminescent solar concentrator. The cool thing is that the light really glows brightly when coming out the edge. And what we've been doing together with Toyota and Tokai University in Japan, the predecessor of these grants, is that then we were putting optical fibers which had neodymium in them and winding them around the edge, yeah? You know, we had Japanese partners involved. You can imagine the origami skills needed for winding up to 400 meters around this frisbee. So this is kind of cool because what we do is we optically pump the neodymium, which has a absorption peak at about 560 nanometers shown there, and we pump these with our dyes. Now you see we don't hit the peak perfectly, but we hit it not too bad. And with that, Our Japanese, so we were doing the optics, they were doing the lasing. Our Japanese partners have demonstrated that we've gone from 1.5 milliwatts up to 15 milliwatts, and now, even after the project ended, they're carrying on there, and they now demonstrated up to 34 milliwatts of lasing, outdoors, sunlight, no electrics needed. So that's kind of cool. So luminescent solar concentrators is, where are we at there? Well, we'd like to get to 10%, and the material is promising for building integrated photovoltaics, but there's a kind of a challenge, right? If you're interested in BIPV, what are you interested in? Well, you'd probably like daylighting happening in your system, right? You'd like some electricity and some daylighting. But to be honest, you can just space the cells 50% in a PV module, and you'll get somewhere between 10 and 12% efficient, and that can be done today. The luminescent solar concentrators I talked about, the 10% was still for an opaque device. Of course, if you want to go transparent, you'll probably go down to maybe 4 or 5% from there. Color is a potential market, and it's a growing market for colored solar products. But there are other technologies on the market like Sunnovation in Germany and Megasol in Switzerland, which is not luminescent, but they're coloring your devices. And at the end of the day, probably they're going to be more efficient than we are. Form is less clear. So with form, I mean bending. You can bend things. It's not really going to be flexible, but you could bend it to a strange shape. But there's kind of a limited market there, I would say. So in a article a few years ago, we also looked at cost estimates. Now, the cost estimates here might shock you that 500 to 1,500 euros per square meter, but this is because we started with triple glazing, and we replaced the middle pane of triple glazing with our luminescent solar concentrator. A lot of the costs actually came from the cost of the perovskite quantum dots that we assumed were going to be used for the technology. It's not really easy to get accurate numbers on the production costs there. And also, it does include transport and installation, etc. Yeah, but it's going to be pretty expensive. Yeah. So, what else can you do? And this is the last few slides. What else can you do with the same materials? So, we then started thinking about, well, you can also possibly enhance the growth of plants via this technology. So, the typical chlorophyll and carotenoid absorption spectrum, and it's a bit like an EQE spectrum for a plant, is shown here. Yeah, it's called the photosynthetic active radiation spectrum, and plant would like to have quite a bit of blue, not much green, and then quite a bit of red light. Yeah, and we were thinking, well, we could try and do something about that. Yeah, because we have lots of green light here in the solar spectrum that's currently wasted. Yeah, so what could we do there? And the answer is 3 things. We could take some of the UV and we could shift it to the blue, which the plant wants. We could take some of the UV and shift it to the red, which is what the plant wants. Or, a little bit more challenging, we can try and take some of the green, which the plant doesn't need, and then shift that to the red as well. So, the other thing that we have to consider here, and I'll emphasize this at the end, the plants are actually fairly complex. Yeah, so I don't want to. The analogy to a solar cell is quite a simple one. But one example, other than that, you can also play around with optically, is that you can increase the fraction of diffuse light, as shown here on the x-axis, and you can see that at least in this case for this plant, and it was tomato growth. The growth rate improved by about 10-20% as the fraction of diffuse light went up. So there's quite a few games you can play in optics. Here we're working with the University of Cambridge, who are making, in this case, they're making some of the optical materials. We're kind of doing the photonic design and optical characterization. And there's a company called Lambda Energy or Lambda Agri, and they're trying to take this product and have it so that you can spray coat that onto the outside of your greenhouse. And this is kind of cool because the materials that have been developed, yeah, they're respectable. They have good UV absorption and good red emission, 70% quantum yields, which is exciting. And even more exciting is that under growth tests, we've demonstrated that you get a 9% enhancement in your basil leaf enhancement if you have with this coating as compared to without this coating. In my lab, again, we're the more inorganic people, at least when it comes to chemistry. So we're trying to make some phosphors, because we believe that inorganic phosphors are going to last for longer under tough solar conditions. So this is an example of a bismuth-doped phosphor, which does a similar job absorbing in the UV, but it gives us this nice blue emission peak shown here. Again, the quantum yields are about 70%. And this we haven't yet, but we would like to start putting this into our own demonstrator scale. I mean, like a meter by a meter greenhouses that we could have on campus. So the outlook there, greenhouses are, and plants actually, are the very complex systems, okay? You need to, when you say light, you have to think about the intensity of the light, the color of the light, and also the amount of diffusivity of the light. When you say temperature, you need to think about air temperature, soil temperature. The same when you go to humidity, air versus soil. And you have CO2 concentration, which plants need to grow. And what I've shown here is just some very rough trends about how these might increase, or the trend as that parameter increases. So here, the material choices, there's probably different markets. You know, some people have these polytunnels, as we call them, and the material might be thrown away every year or 2 years. It's a huge amount of waste. For that, organic dyes, put them in the polyethylene sheet and extrude it. It's probably simple. What we're targeting is more longer life greenhouses where they might be made of glass, or there's a new development with ETFE greenhouses, which are designed to last more like 25 years. And then our inorganic materials might have a better, be more competitive. Overall, we're starting to look at the overall net zero energy consumption concept for a greenhouse. You use energy for heating, ventilation, etc. We're trying to get that down to net zero. And one thing I touched on very briefly at the end is this concept of passive daytime radiative cooling, where you can achieve 6 degrees cooling in this model greenhouse compared to the standard glance greenhouse. And with that, it brings my talk to the end. I would like to acknowledge some of the many funders of this work over the years, to thank a lot of the people who did the work, my team. I'd like to point out here that this was taken at our team retreat in the Austrian Alps, and this was inspired by Rob Largen's cross-country skiing trips way back in the year, I don't know when, at UNSW. And with that, considering the current situation, thank you and peace be with you.
Thank you very much, Bryce. I think of all the people I know who works on these things, you've really covered the whole sort of gamut of approaches. So, folks, got time maybe for one or two questions?
Yeah, sorry, I went long.
No, it was good. Michael.
Thank you so much for the talk. So, in any spectral conversion system, you obviously have something that's absorbing, something that's spectrally converted, something that's emitting, and these might be all one system or multiple systems. And in down conversion, you demonstrated, a few marrying of systems to solve the problem of lanthanide's terrible absorption, but good conversion and emission. Do you foresee any similar opportunity in up conversion by marrying with some kind of antenna effect?
Good question. Well, the antenna effect I kind of covered, but I called it something different. In that sense, I called it sensitization, right? And why I'm using a different word, because the antenna effect is usually used by the organic community. But once you get down to those wavelength ranges in the near infrared, organics tend to stop working well. And why? Because of the huge amount of vibrational energies of your carbon-carbon, carbon-hydrogen, and the overtones of these is huge amounts of vibrational energy that just leads to non-radiative recombination. So I think the opportunity for sensitization I gave the example of using nickel as a near-infrared absorber. Yes, it can work. Yes, it can help, but by a factor of 2, right? And we're not looking for 2. You're looking for 100 or 1,000. Yeah? Thanks.
Any more questions?
Oh, yes. Yes, thank you so much for your slide. So it's really useful. So, I just have more question about measurement, like the measurement of the PLQY. So, yep, I saw in the slide that you mentioned you try to repeat the perovskite system for achieving over 100% of the PLQY, but it's really challenging. And then you mentioned one of the reasons maybe due to the measurement stuff. So I just really curiously how you do the calibration and then measurement for the PLQY, and then especially when you do it, you just you see any difference between measuring the raw material in the powder or in the liquid form with like the PLQY of the material, but maybe for example in the film-based form. So
I'll answer the second one part of your question first. So yes, you see differences. You see differences largely due to absorption. Okay, so if you have a powder, what we've found, it really depends on who puts the powder, who packs it in the cuvette. If you do it, if I do it, the answers can easily vary by a factor of 2. But I guess the good news at the end of the day, yes, we often measure powders because it's convenient, but it's not the end product. You don't usually want to work with a powder and a technology, yeah? Where it also becomes important, though, is that in that case, or in some cases, if you have powders that are scattering and you have them in a film, you find that actually scattering can work for you and scattering can work against you. So scattering can actually help the coupling of light and increasing the absorption within a film. Or it can actually scatter. If there's too much scattering, it might scatter photons away that you want. To come back to the quantum yield question, I think, so normally we do calibration with a calibrated tungsten lamp, but you have to think that a tungsten lamp is not particularly strongly emitting in the UV. There's some, but you have to be really careful. And then you have to consider what you're trying to do is you're trying to absorb 300 to 400 nanometer photons, and you're with the same spectrometer, you're trying to look at the 1,000 nanometer photons. So you've got a silicon CCD that's really operating across its whole range and really on the edges of its spectrum. And I know from our experience, I can't speak for Gamelin's group, but I know from our experience, sometimes when we get a stray result, we're like, we should check the calibration on that, and it matters. Yeah, so it's really the calibration of the spectrometer is key in the whole quantum yield measurement. Thank you.
Thank you. And Bryce, perhaps actually on that point, I mean, measuring quantum yield, I think, is deceptively difficult.
Agree.
And
the equation's so simple, the equipment's so simple.
Exactly.
but
the practice is not.
Yeah.
And so, I'm wondering if there might not be an opportunity to have almost like a sort of round robin activity, because we do this for solar cell calibration.
Well, we've done it for upconversion materials.
Right.
And interestingly, we learned that the certified calibration lab in Germany, they got one of their lenses wrong in their system. So their results weren't agreeing with us and the Dutch, right? But okay, but that's fine, then you find the problems, you do it in 3 labs, and we got very similar answers. Yeah. Now for upconversion, it's even tougher because it's non-linear, right? But for this down conversion, this would be definitely of interest.
Yeah.
Yeah.
Well, that might be actually a good thing for us to then establish is,
Cool.
to do a bit of a European, Australian, and anyone else who wants to participate, just, yeah.
Yeah, because we've already been doing these with Rebecca's group at 20,
Yeah.
right? And there was a group in Monash, actually, I forgot the name of the professor there. Sorry, slipped my mind. Pardon? Okay, thank you. Who was so excited when they sent us this material. But it's also not 200%. Yeah. So, but as I mentioned there, that what's really cool is the developments coming with that Freddie Rabouv is pioneering there, because then you can really look at the mechanism. Yeah, this I really like.
Me too.
Yeah.
Yeah. No, that looks great.
Okay.
Victor, final question.
Thank you, Bryce. You mentioned that for a lot of the quantum cutting materials, there was this power saturation, or it's nonlinear. and it doesn't work under one sun. Did you?
That was specifically the case for this material that we've just been talking about, the cesium lead fluoride doped with the ytterbium.
You're right. So does it happen to most quantum cutting materials
No, most of them are linear.
with ytterbium?
Yes, even if they have ytterbium. I think the difference here is that there's probably a trade-off in the amount of ytterbium you introduce. You probably want quite a bit because it's your emitter, but every time you introduce an ytterbium ion, you also introduce at least a defect. I'm not the expert here, and I suspect this is what's happening. Yeah, I haven't really so much yet looked into the photophysics of this.
Yeah, there is a concentration quenching, I believe. That's
Yeah, the concentration quenching is known, so people suspect that 20% ytterbium is the optimum. Yeah, but somehow in this field, it has a feeling there's quite a bit of alchemy around it, yeah? And like I said, we've just spent 2 years trying to recreate the results and have failed. And I think now is the time, maybe like Ned's suggestion, to say, okay, is that what you're getting to in other labs? And then perhaps even more importantly saying, well, hang on, what's really happening here as the mechanism? Yeah.
one more question. So about the core shell structure, core shell
nanocrystals, which I didn't really talk about today. Yeah.
Yeah, on the either downshifting or down conversion, and you also mentioned that the absorption can be very low. Do you think it's still useful as a down converter?
Yeah, I think there you can, you might have heard that you can have core shell systems, so you can actually play around with the architecture of the system. And perhaps other elements like cerium or bismuth or what could be used as a sensitizer to then transfer the energy to that rare earth ion that you're trying to get to do the down conversion process. But I'm not speaking so much there from experience yet. But it's kind of planned or wished for. Yeah.
Thank you.
You're welcome.
Okay, well, I think that's a great point to end on. So, Bryce, thank you so much. Great seminar and great to see you again.
Thank you, Ned. Yeah, and thank you all for your interest and attendance.